Now that we have an idea of differentiating vector-valued functions, let's talk about integrals for vector-valued functions. Just like the antiderivatives we worked on with scalar-valued functions, we can define the antiderivatives for vector-valued functions in the following way. Given the vector-valued function r is equal to fi hat plus gj hat plus hk hat, the antiderivative for the vector-valued function r is given by the vector capital R is equal to capital Fi hat plus capital Gj hat plus capital Hk hat, provided that the derivative of the vector function capital R is equal to the vector function little r, and that capital F, G, and H are antiderivatives of little f, g, and h respectively. If I take the set of all the antiderivatives for the vector r, I will get the indefinite integral of the vector r. I can write it as the indefinite integral of the vector r of t dt is equal to the vector capital R of little t plus the vector c, which is an arbitrary constant vector. So let's work some examples. I want to compute the indefinite integrals for the vector function r of t is equal to the components 5 times t to the negative 4 minus t squared, t to the 6th minus 4t cubed, and 2 over t. The second vector-valued function I want to compute the integral for is r of t is equal to the components 2 to the t, 1 over the quantity 1 plus 2 to the t, and natural log of t. I take the integral of the first vector, the indefinite integral of r of t dt is equal to the indefinite integral of the quantity 5t to the negative 4 minus t squared dt in the I hat direction, plus the indefinite integral of the quantity t to the 6th minus 4t cubed dt in the j hat direction, plus the indefinite integral of 2 over t dt in the k hat direction. This gives me another vector-valued function that is specified by the components negative 5 over 3t cubed minus t cubed over 3, t to the 7th over 7 minus t cubed, and 2 times the natural log of the absolute value of t, plus the vector c, which is an arbitrary constant vector. For the second integral, I take the indefinite integral of the vector r of t dt, which is equal to the indefinite integral of 2 to the t dt in the I hat direction, plus the indefinite integral of 1 over the quantity 1 plus 2t dt in the j hat direction, plus the indefinite integral of the natural log of t dt in the k hat direction. This gives me another vector-valued function specified by the components 2 to the t over the natural log of 2, 1/2 the natural log of the absolute value of 1 plus 2t, and t times the natural log of the absolute value of t minus t, plus the vector c, which is an arbitrary constant vector. Now, if I'm given an antiderivative, r prime of t, I can find the vector-valued function r of t using integration. So here I have r prime of t specified by the components 0, 2, and 2t, and I'm also given a condition that says the vector r evaluated at 1 is equal to the components 4, 3, negative 5. I set up an integration where r of t is going to be equal to the indefinite integral of 0 dt in the I hat direction, plus the indefinite integral 2 dt in the j hat direction, plus the indefinite integral 2t dt in the k hat direction. I do the integration, and I find that my vector r of t is equal to 2t j hat plus t squared k hat plus the vector c, which is an arbitrary constant. But now I use the condition that r of 1 gives me the components 4, 3, negative 5. This allows me to write an equation specified by 4i hat plus 3j hat minus 5k hat is equal to 2 times 1 j hat plus 1 squared k hat plus the vector c. I'm going to solve this for my arbitrary constant vector c, and I find out that my vector c is equal to 4i hat plus j hat minus 6k hat. This allows me to write my vector r of t as 4i hat plus the quantity 2t plus 1 j hat plus the quantity t squared minus 6 k hat. If I want to compute a definite integral using vector-valued functions, I simply apply the fundamental theorem of calculus just as I did before when I had scalar-valued functions. The only difference is that I have to keep track of my vector components. So if I let r of t equal f of t I hat plus g of t j hat plus h of t k hat, where f, g, and h are integrable functions on the closed interval from a to b, I can write a definite integral by taking the integral from a to b of r of t dt is equal to the integral from a to b of f of t dt in the I hat direction, plus the integral from a to b of g of t dt in the j hat direction, plus the integral from a to b of h of t dt in the k hat direction. All that's left is to integrate each piece term by term and apply the limits of integration. So let's work some examples. I want to evaluate the following definite integrals. First, I want to evaluate the integral from 1 to 4 of the vector with components 6t squared, 8t cubed, 9t squared dt, and I want to evaluate the integral from 1/2 to 1 of the vector with the components 3 over the quantity 1 plus 2t, 0, and negative pi times the cosecant squared of pi t over 2 dt. For the first one, I'm taking the integral from 1 to 4 of a vector with the components 6t squared, 8t cubed, 9t squared dt. And this is going to be equal to the integral from 1 to 4 of 6t squared dt in the I hat direction, plus the integral from 1 to 4 of 8t cubed dt in the j hat direction, plus the integral from 1 to 4 of 9t squared dt in the k hat direction. Doing that integration piece by piece, I get 2t cubed I hat plus 2t to the 4th j hat plus 3t cubed k hat evaluated from 1 to 4. I plug in the limits of integration. I get 128 I hat plus 512 j hat plus 192 k hat minus the quantity 2 I hat plus 2 j hat plus 3 k hat. I combine like terms and I get the vector 126 I hat plus 510 j hat plus 189 k hat, and in component form gives me the component vector 126, 510, 189. For the second integral, the integral from 1/2 to 1 of the vector with components 3 over the quantity 1 plus 2t, 0, negative pi cosecant squared of pi t over 2 dt is equal to the integral from 1/2 to 1 of 3 over the quantity 1 plus 2t dt I hat, plus the integral from 1/2 to 1 of 0 dt j hat, plus the integral from 1/2 to 1 of negative pi cosecant squared pi t over 2 dt k hat. I do that integration and I get 3 times the natural log of the absolute value of 1 plus 2t divided by 2 in the I hat direction, plus 0 in the j hat direction, plus 2 times the cotangent of pi t over 2 in the k hat direction, evaluated from 1/2 to 1. I plug in those limits of integration, and I get 3 times the natural log of 3 over 2, 0, 0, minus 3 times the natural log of 2 over 2, 0, 2, which is equal to 3/2 times the natural log of 3 over 2, 0, and negative 2. So now you get to try it. Pause the video and evaluate the following integrals. When you're ready, restart the video to check your understanding. The first integral is an indefinite integral for the vector specified by the components square root of t, cosine of pi t, and 4 over t dt, where I'm given the vector r of 1 is equal to the components 2, 3, 4. The second integral is the integral from 0 to pi over 4 of the vector secant squared of t, negative cosine t, negative 1 dt. For the indefinite integral of the vector specified by the components square root of t, cosine pi t, and 4 over t dt, I'm going to integrate that term by term. This becomes the indefinite integral of square root of t dt in the I hat direction, plus the indefinite integral of cosine pi t dt in the j hat direction, plus the indefinite integral of 4 over t dt in the k hat direction. I do that integration, and I get a vector with components 2 t to the 3/2 divided by 3, sine pi t over pi, and 4 times the natural log of the absolute value of t, and then I add the vector c, which is an arbitrary constant vector. But I have the condition that my vector evaluated at 1 gives me the components 2, 3, 4. I can set this up to solve for my arbitrary constant vector. The vector components 2, 3, 4 will be equal to the vector components 2/3, 0, 0 plus the vector c. This means that my vector c is equal to the components 4/3, 3, and 4, which makes my vector r of t equal to 2/3 t to the 3/2 sine pi t over pi and 4 times the natural log of the absolute value of t plus the components 4/3, 3, and 4. Combining those terms, I get my final result. The vector r of t is equal to the components 2/3 t to the 3/2 plus 4/3, 3 plus sine pi t over pi, and 4 plus 4 times the natural log of the absolute value of t. The second integral is a definite integral. I want to find the integral from 0 to pi fourths of the vector with components secant squared t, negative cosine t, and -1 dt. Again, I take the integral term by term, and I get the integral from 0 to pi over 4 of secant squared t dt in the I hat direction, minus the integral from 0 to pi fourths of cosine t dt in the j hat direction, minus the integral from 0 to pi over 4 of 1 dt in the k hat direction. This gives me tangent t I hat minus sine t j hat minus t k hat evaluated from 0 to pi over 4. Plug in the values for t, and I get the vector I hat minus square root of 2 over 2 j hat minus pi fourths k hat minus 0 I hat minus 0 j hat minus 0 k hat. My final result is that my vector r of t is given by the components 1, negative square root of 2 over 2, and negative pi over 4. This is how I can use the rules of integration and the fundamental theorem of calculus to compute the integrals of vector-valued functions. If you're asked for an indefinite integral, be sure and include the constant vector c, and then if you're given any initial conditions, you can solve for that. Let me know if you have any questions.